Okay, welcome back, everybody. Hope everybody had a good weekend. Here, let me admit here. I met a couple more people. Okay. Before we begin, any questions, comments, concerns? I'm in the process of catching up on my grading. So some of the assignment. Oh, a quick word, Canvas. Canvas treats everything as a quiz. Anything you do online as a quiz. So, but we label them individually as homework, exams, or whatever activity. But Canvas just treats everything as a quiz. So homework is a quiz as per Canvas nomenclature, naming, and exams are a quiz. Okay. That's just the way Canvas treats everything. Okay, FYI. Also, there's some things that you fill in. I haven't graded yet, so you may not see your full score until I get it done. So I get it done as soon as I can. So there are some couple of them I need to go and check. Anything, let's see, anything else? No, I think I got everything. All right, well, if there are no questions, I will continue with where we ended. We'll be done with this chapter and then jump right into chapter 2. We ended up on slide 35, but I just go back one. We're talking about the physical states of the elements, 118 elements, okay? Of the 118 elements, only 2 of them are liquids at 25 degrees Celsius, which is about room temperature, and at one atmosphere, which is about here, 1 atmosphere here. If you go up to, say, Colorado, less atmosphere, pressure is much less, okay? But at 1 atmosphere, 25 degrees, the elements mercury and bromine are liquids, okay? We have about 12 noble gases. Okay, and I'll explain what the noble gases are again to refresh your memory, but they are in group Roman numeral 8A. Noble gases because they are very inert and they don't react. Okay. Also, you have H2, subscript 2, N2, O2, F2, and Cl2. Hydrogen, nitrogen, oxygen, fluorine, and chlorine. These are some of the diatomic elements. These are elements that do not exist singly as one atom. They have to combine because of stability purposes with another of itself to be stable. Okay. All right. Mallory, my voice is a little bit, let me check my, I may have to close some, is everybody hearing me okay? It's
Yeah.
kind of lagging a little bit. What I'll do is let me close some applications and that might help. I did have a number of things going on in the background. Okay, let's see what happens if this helps. Okay, so these are noble gases, and then all the other elements are solids. Okay, so this particular periodic table demonstrates the physical property of the elements at 25 degrees 1 atmosphere. Those in yellow are all gases. Okay, so you have these we call the noble gases right here, the last column. Note that there's Roman numerals on top for the column. We go to the far left over here, you got 1A, Roman numeral 1A, Roman numeral 2A. Now in here, they have the B after them. There's a totally, this group of elements have their own special name. We'll talk about those at length. And then we go across with 3A, 4A, 5A, 6A, 7A, and then finally 8A, okay? Now, with the exception of helium, which is sitting right here, what all of these noble gases have in common is that they have around the outermost layer, We're going to learn about electrons being in different energy layers. In the outermost layer, they have 8 electrons. That magical 8 number that's going to be repeated over and over again. We will find that the driving force of these elements in any type of reaction that's occurring, the driving force is to obtain that magical 8 number, meaning there's 8 electrons around the outermost shell, which is the most stable form for these elements. And that's why these gases, noble gases, are called noble gases, because they are inert. Now, helium, its magical number is 2. It has 2 electrons around the outermost shell. Everybody else has 8. Okay, so notice there's 7, 1, 2, 3, 4, 5, 6, 7 noble gases. 7, 8, 9, 10, 11, and 12 elements that are gases. Okay. And then the 2 that are liquids, there's mercury sitting right there. And then bromine, I kind of marked it up a little bit, sitting right there. So we got 2 elements that are liquids. Okay. And the rest in blue color are all solids. So you can, by glancing at the periodic table, determine the physical property at 25 degrees, whether an element is a solid, liquid, or gas. That means if somebody points this one, even though you may not know what it is, but it's element 45, you can see its position and say it is a solid, or it is a liquid, or it is a gas. Okay. Now, these diatomic elements, these are the elements that, for stability purposes, actually combine with another element of itself. If they were to combine with another element that's different, then it's no longer an element. Now it's a compound. Remember, by definition, a compound is made up of 1 or 2 or more different elements. So when 2 elements are the same, combined, and they have to have 2 of them, we put a subscript. So H2, what we're trying to show there is that there is a bond, which we designate with a line, okay, like this. Okay, all these are bonded either with a single bond or a double bond. We'll talk about how they're bonded, but there's a bond between the 2 different elements. And instead of having draw it out like this all the time, we put a subscript 2, which tells us there's 2 atoms of the element. So we have 7 elements that are diatomic. So we use this have no fear of ice cold. If you want to call it beer, or you can call it beverage, it makes no difference. So the H, if have, is for hydrogen. The N in no is for nitrogen. The F in fear is for fluorine. The O of is for oxygen. The I in ice is for iodine. Okay. The C in cold is for chlorine, and B is for bromine. Okay. And they exist as diatomics, denoted by the following models there. Okay. Diatomic elements. Now, there are 3 types of elements. One type, number 1, is the metals. Okay, we're all familiar with metals, iron, aluminum, and so forth. Then we have non-metals, okay? And then we have some that are called semi-metals or metalloid. And what they when we call them semi-metals listed up here, is they have properties of metals and properties of non-metals. Okay, it is like a mule. You know, if you don't know what where a mule comes from, it's a combination of a horse and a donkey. Okay, and the mule has the properties of a donkey and the properties of a horse, and that's what a semi-metal is, or a metalloid. Now, non-metals are located on the right side. There is on the periodic table what we call a stair step. Let me clear this up here real quick and back it up for a second. And that really helps us out with respect to determining where the metalloids are. Let me pull up the periodic table that we normally use. Notice that stair step here in dark colors, like a step on the right side. Okay, right here, this direction right here. Okay, that is our reference point to determine who are the semi-metal. Okay, and everybody to the left of the stair step are metals. And everybody to the right of the stair step are non-metals. The one exception to the left is H over here in the far left, hydrogen. Hydrogen is a gas, it's a non-metal. Okay. All right, so that's our reference point, that stair step. And so their non-metals are located to the right. Semi-metals are touching the stair step, okay, except for aluminum, which is the metal. And then metals are to the left side of that stair step, with the exception of hydrogen. And so here are the ones in green, starting with boron, going in this direction. These are the non-metals. This one, number 17, is in white. It's kind of brand new metal. We're trying to determine where it sits as far as its properties. My guess is number 117 will probably end up being a non-metal. Okay. Now everything in red are the non-metals, including hydrogen way over in the left. And that means that everything else in blue is a metal. Now the takeaway from here, now we're not going to do a lot of work on semi-metals. Okay, we're not going to do a lot of work for that. We're going to do most of our work, or you're going to be with the interaction of metals and non-metals. Okay, now we need to know who's a metal and who's a non-metal. Why? Because that's going to help you define the type of the compound that you're working with. Okay, we are going to learn that when you have a combination of a metal bonded with a non-metal, well, you're going to have one type of compound, and then the other combination would be a non-metal bonded with a non-metal. Okay. So for example, look at water, H2O. Okay. Water is a combination of two different elements, right? Hydrogen and oxygen. Hydrogen is a non-metal, oxygen is a non-metal. Okay. That puts water in a special category of type of compound. Let's take a look at an example of a metal and non-metal, something you put on your French fries. Sodium chloride. Okay. Sodium is a metal and the chloride is a non-metal. See that combination? And once we determine that that's the combination I work with, that means that sodium chloride is a very specific type of compound. And there are only two types of compounds. And that is, the first type is a combination of metal and non-metal. And the second type is a combination of non-metals together. And that, once we identify that, opens up a whole slew of other information. Okay, so it's important that we understand who the non-metals are and who are the metals. Another thing to put in your long-term memory with respect to metals and non-metals, when we start talking about reactions, all of the metals want to lose electrons. Okay, lose electrons. All of the did they say non-metals? Excuse me. All of the metals in blue, everybody here in blue, they want to lose electrons. Okay. And I found out that my pen is and Zoom are not getting along. It gets along fine with all of the other applications, but not Zoom. And all of the non-metals, if the metals want to lose electrons, guess what? The non-metals want to gain electrons. And that concept helps us understand, will help us understand why certain elements end up with a negative charge and certain other elements end up with a positive charge. Okay. So it's all tied in together. All right, properties of metals in general, they have shiny appearance. Okay. They are very soft. The pure metals, they can be stretched out. A lot of the copper, for example, a lot of my research dealt with copper metal. We used to get metal from Europe in 1/4 inch or 7 millimeter thickness, but before it started like that, it used to be maybe about 2-3 feet thick, and it would be rolled back and forth until it got it down to a 1/4 inch or 7 millimeter thickness. So it's very ductile, it can be stretched out. Metals. All of them are solids. All metals are solid with the exception of mercury. Okay, and their density, remember that ratio of mass over volume, tend to be high. Melting points, very high melting points. Okay. And metals, due to the property of them having a lot of electrons around the surface, are good conductors of electricity and also means they're good conductors of heat. With respect to non-metals, in general, they have dull appearance. Okay. If they're solids, they're very brittle solids, not very hard, breakable. A lot of the non-metals are gases, and their density in general, relative to the metals, is relatively low, usually low. And they tend to melt at a much lower temperature than metals do. And with respect to conductivity, because they're not very full in electrons, as compared to metals, they're very poor conductors. They're better insulators. The fact that they're poor conductors, they're better insulators. Okay. So what we're going to take away from this particular chapter is this. One, we talked about be familiar with at least the first 20 elements with respect to their symbol and their name. Okay. And you might as well start getting used to their number. Each one has their number, okay, atomic number. Then we also gave a list of other about 10, 15 additional elements, okay? Be familiar with those. And then being able to determine, in this case, for any element, whether it's a solid, liquid, or gas, okay? And I direct you to slide number 35. It breaks it down for you as far as which elements at 25 degrees and 1 atmosphere are solid, which are liquids and which are gas. Okay. Again, from their position on the periodic table, determine which elements are metal, who are the non-metals, and if necessary, which ones are the semi-metals, okay, or metalloids. You may hear them use that term. Okay. And there's only 7 elements that are diatomic. Have no fear of ice cold beverage. Okay. Be familiar with those. And that's important too, to determine that, because when we start writing chemical reactions, we're going to be given chemical reactions in words. And like, for example, you might say something, sodium metal in the presence of chlorine reacted to produce sodium chloride. We're going to take that sentence and convert it into a chemical reaction. And it's reacting with chlorine, that tells us it's diatomic, okay? It's one of the diatomic, so we would put it down as Cl2. Let me introduce something here real quick, because when we talk about chlorine versus chloride, okay, we say chlorine, okay, versus chloride. Big difference, humongous difference. The I&E is talking about the element, okay? earlier I said, and chlorine in this case, and this is true for bromine, fluorine, iodine, the ones in group Roman numeral 7A. These guys have their own special name, but when they're the elements, they have the INE suffix. Okay. They're also nonmetals, and remember I just stated nonmetals want to gain electrons. And so chlorine, fluorine, bromine, they have a tendency to gain electrons. And when that happens, we change the name to chloride. This is part of the nomenclature, naming the compounds. And so you wouldn't say sodium chlorine, that would be totally incorrect, but you would say sodium chloride, because that tells you that the chlorine has reacted to form what we call an ion and pick up an electron. But much more on that later on. So I just give you a little taste of what's coming. Okay. All right. So with that, congratulations. You're done with chapter 1. All right. Any questions? Okay, there's a question. Is my voice still kind of, Mallory, is it still kind of laggy for you? Okay, well, as long as you guys can hear me, okay. All right, so let us kind of step out of chemistry a little bit. And we're going to talk about the little mathematics, okay, some math skills. You know, it is science. And so, all right, thank you, Karen. It is science, so we have to do some mathematics. But like I said before, we're not doing anything complicated. We're not doing differential equations, matrix algebra, nothing of the sort. Add, subtract, multiply, divide. Some very basic algebra. Okay, very basic algebra. So, but more importantly, is learning a technique to be able to convert from one set of units to the other, because this technique we're going to utilize to further down the road when we start looking at calculations and figure out doing chemical calculations. Okay. All right. So chapter 2 is practice problems. So, you know, please jump in there and knock them out as soon as you can, help you out. So measurements. Okay. Obviously, what we utilize in science is we use the metric units. Now, but excuse me, we also think to remember about this is that, you know, if the statement a book weighs 8 really doesn't tell you anything. Without units, that sentence doesn't tell you that 8 pounds, 8 tons, 8 millimeters, 8 milligrams. Okay, we gotta put units. Every measurement, every type of measurement, when we talk about measurements, we're talking about measuring the length, we're talking about measuring the mass, and we're talking about measuring the volume. Okay. Now, every measurement has a degree of uncertainty. There is nothing out there that is 100% correct. That last digit, there's always a degree of uncertainty. Okay. Okay, Mallory, it's still acting up, huh? Okay. All right, if you have to, do what you got to do. I just read your message. So all measurements have a degree of uncertainty, and that last number is a guess, you know, and that last number in any type of measurement is, you're not going to be correct or incorrect, because it's subjective. Meaning, if I'm measuring something, I may have to guess on that last number, you know, like 1.5 compared to 1.55. Obviously, the 0.55 is a little more accuracy. Okay. All right. So for length, let's talk about the units that we're going to utilize. Once we're done with this, there's been a whole thing of metric units that will help. I will go over if we have time. And because metric units sometimes can be very challenging, which is ironic because since I was a kid, it was like 100 years ago, we've been trying to convert to the metric system. And we're still not there, you know. But yet, you can go to the grocery store and buy a gallon of milk, but then if you buy soda pop, it's a 2-liter bowl. Figure that out, right? All right, so length, we use the units given up here, cm, which stands for centimeters, mm, which stands for millimeters, m for meters, and km for kilometers, okay? Now, what we measure with, obviously, we can use rulers, and some rulers are a lot more accurate than others. It just happens to be the degree of how many little units you have in there. You can see the white ruler here, there's a degree of uncertainty, much more uncertainty for the white one, okay? Let's say we wanted to measure a point. Oh, I don't know, somewhere in here. Okay, something like that. Well, if you look at the white one here, the white ruler, we're only accurate to at least the 10th unit. So, it might say 4.5. Yeah, I don't know. What do you want to call it? What would you call that line? Let me see if I can clear this up a little bit. Put something a little bit more. Let's say we wanted to measure that with two things. Okay, so, what would you say that first, using a white ruler, well, what kind of measurement would you guess? I got a 4.8. I just made the mark someplace else. So, yeah. Sorry, Karen. What would you say is the new mark, the new yellow mark? Best guess. Okay. 3.6, maybe? Yeah. Okay. Now, be careful with the accuracy here. Okay. Using the white ruler, you can only be as accurate as the 10th place. Okay. And so, yeah, I would say that's reasonable, 3.6. And let's assume we're talking about units here, millimeters, centimeters, okay? 3.6, but down at the bottom one, can we not be a lot more accurate? We got 3.6, and now we got, what would you guys say, using this one, the brown ruler, what would you say? Maybe 6.2, maybe? Would you agree? That last number, is a guess, your best guess, and it could vary. Your last number there could be 1, which is fine. And that's reasonable because it all depends on how you read it, the last number. But the point here is that the white ruler, you can only be accurate to this 10th place, the 10th place. Whereas here, the brown one, you can be accurate to the 100th place. So the bottom brown ruler is a lot more accurate, okay? And so to give a measurement of 3.61 using the white ruler would be incorrect because you don't have that accuracy with respect to the tool that you're utilizing, okay? Everybody see that? So your tool defines your accuracy. If we were using a laser beam to do a measurement, yeah, the laser beam could probably give us maybe 3 decimal places, a lot more accurate as far as the measurement. Okay, so be aware of the accuracy of the tool that you have because that determines how many decimal places you can use. And the whole point of this is this. We all know that you can type and multiply numbers on your calculator, and you can end up with 50 digits, right? And people would be tended to say, I'm going to print out my 50 digits as an answer. But that would be incorrect. And why that's incorrect is this, because your answer cannot be more accurate than the least accurate method of obtaining that answer. Okay? And so if you're only accurate to the 10th place, then you can't give an answer that's accurate to the 4 decimal places because you didn't measure it that accurate. And this is what this whole chapter is all about, being able to understand that and comprehend it. Okay. All right. So, which has more uncertainty? Well, the bottom one, because the white one, I should say, excuse me, is only accurate to the 10th place, whereas the brown ruler is accurate to the 100th place. So there's more uncertainty with respect to the white one than there is to the brown ruler. Now, mass, we use units like mg, which is milligrams, or kg, kilograms, and then g per grams, okay? Now, we look at the ruler here, the measurement tool here, these are balances. The one on the right is a electronic balance. And you can look at the numbers, it looks like 18.7954. You're up to 4 decimal places. And the one on the left, that's a triple, we call it a triple beam balance. Not as accurate, maybe 100 place, okay? And so again, if we need to present an answer and we're using the balance on the right for our numbers to do whatever calculations we're going to do, then yes, we can present numbers to the 4th decimal place if we're using the instrument on the right. And on the left, we have to change the number of decimal places, okay? I talked about this in the first day where we talked about mass versus weight, because weight is a measure of gravity. And so somebody here, our nerve weighing 170 pounds is about almost 29, 30 pounds on the moon, simply because of the gravitational force on the moon versus the gravitational force on the earth, different gravitational force. The equation that relates mass and weight is given there, where you got weight is equal to the mass times the gravity for whatever body you're on. And since we're on Earth, it's 9.8 meters per second square, I believe, for on Earth. But since we are on Earth, we tend to interchange the term mass and weight. So, okay, volume. Well, there's some a picture here of different types of pieces of equipment that we utilize to measure volume. And units, normally the most common unit is the capital L for liters, but we also use kiloliters and milliliters. Okay. Syringes, you may be familiar, some of you may be working in a hospital and you talk about giving, 10 cc's or something. Well, we're talking about cubic centimeters, okay? Cubic centimeters. And here's your first conversion factor. There's 1 milliliter is equal to 1 cubic centimeter or 1 cc, okay? And so we need to convert, if you're given, units of cc, I need to convert to milliliters. It's a simple 1-to-1 relationship. Okay, give me 1 second. I need to pull up the file. And bear with me for a second, please. All right. Okay, I'm going to have to find it later and I'll share it with you next time. All right, let's say, for example, we need to convert this. I like this because it helps me out. We got metric units and we have English units. And within the English units, which is this, I always had trouble with cups and pints and so forth, but this kind of helped me out here. So you may have seen it someplace somewhere. So if you notice, we got the big G on the outside, right? Okay, that represents 1 gallon. So 1 gallon is equal to, and there's 4 cubes within the gallon, so that is equal to 4 quarts. Okay. Now, if you look inside the quart symbol, there are 2 P's. Now, that means that 1 quart is equal to 2 pints. Okay. And if you look closely within the pint, the P, you have 2 C's. So that means that 1 pint is equal to 2 cups. Okay. 2 cups. So I have these conversion factors. 1 quart is equal, 1 gallon is equal to 4 quarts. Now, what I can do now is this, depending on the problem, I can write this ratio with gallons in the numerator. Okay. Or I can, or I can put gallons in the denominator. And I have this factory here that I may need to multiply. Now, if I'm going to multiply, if I have, say, 10 quarts and I need to convert that to gallons, well, I would utilize the factor on top. Why? Guess what? When I multiply this, my quarts cancel, and I end up with the units that I need in gallons. And if I'm given gallons and I need to convert to quarts, guess what? I use the bottom factor, okay? And I might need 10 gallons. I need to convert that to quarts. Notice how my gallons cancel out. So I got 40 quarts in 10 gallons. And this is how we're talking about our units. Every conversion factor is a ratio that I can write 1 or 2 ways. Now, you might be tempted to take that 4 and then make, say, call this 0.25 gallons per quart. Okay. If you can keep track, I don't recommend doing that, but if you can keep track of your numbers and that's how you're comfortable with, then go for it. I just keep the numbers intact, okay? And don't worry about converting the factor. Just leave the numbers intact, put them up in numerator and denominator, whichever the way you need. Down the road, when we are doing chemical calculations, you're going to set up factors as follows, like this. And you're going to be able to convert from apples to oranges as an extreme example, right? I do have an extreme example that I'm going to show you here in a bit once we're done with this. All right, volume. Now, how do we measure volume? Well, there's something unique about most liquids is that when they're put in a cylinder, they tend to concave, have what's called a meniscus, okay? And the way we read that is you look at the meniscus and you're looking from, oh, let me clear that for a second. You read the bottom of the meniscus. It's a little bit angled there. Sorry about that, but you're over here and this represents your eye over here and you're looking across, okay? Looking across. So you read the bottom of the meniscus. And also when you read volumes, be careful, look at the container. This container 0 starts at the bottom. There are some volume measurement containers, the 0 starts at the top. So be aware of which direction you're reading. So you're reading here, I know 20, and then the number here 20, what would be 22? Where are we looking at? Units of 1, 21 point. Your guess is as good as any for the last number, maybe 0.5. Okay. Not the other way around, reading from this direction would be incorrect. So be aware where your 0 mark is, and so you're reading the right number, okay? But you read the bottom of the meniscus. All right, which brings us to this concept of significant figures. Now, the takeaway from this group, this section is this. When we talk about significance, we are not talking about, okay, that number doesn't count. And then in the calculation, we're going to be doing calculations. And so we cannot, when we say significant, we're not talking about, it doesn't count, we don't need to use it. Not that kind of significance. It brings us back to significant with respect to our final calculation. And the comment I said earlier was when we multiply and divide or add and subtract, that our answer should not be more accurate than the least accurate number that you utilize in that mathematical function. Okay, and so what we have to determine how many significant digits, significant numbers are in the numbers that you're utilizing to do the calculations. Okay, so that's what we're talking about, being significant. All right, so if we look at something like a bathroom scale, or like using the examples that we just did earlier about measuring, here we got a surgical scale or a electronic balance versus one of these triple beam balances. You know, obviously the surgical scale here is a lot more accurate, right? And therefore we'll have more significant figures, significant numbers, because it has more accuracy in its measurement. Back to what we did earlier in this example, here we're taking a measurement. Now, what would you say? What would be the value for the top ruler? What would you guys think? Obviously, in both cases, 29, but what would be for the top? What kind of measurement would that be? 29 something? Would you agree at say 29? What we got? All right, now 0.2 would be a good number, but not the 0.3. Remember, we can't get that accurate. Okay, our accuracy is only dependent on the increments that were given here. We have no increments between the numbers, and so that second number after the decimal point, we're given the best guess. Okay, it could be 0.2, which is a good number to get. Down at the bottom, notice we got more increments in between the numbers. Okay, so we can be a little more accurate because we know for sure now that is 29.2. But then now, because it has more increments, I can guess at the next number in 100 place. So I don't know, we'll call it 0.2 if you like. Okay. So 29.2223. You wouldn't be incorrect, you know, in any one of those numbers that for the last digit, but you can see here that the first one had 3 significant figures. 3 significant figures, the 2, the 9, and the 2, whereas the bottom one has 4. I'm just going to shorthand it, SF, significant figures. Okay, so obviously the bottom number is a lot more accurate. Now, if for some reason I needed to do some mathematical function between these two numbers, then my answer could not carry more significant digits than the least accurate, which would be the top one. Okay, that's the whole ultimate goal that we're doing. All right. So we have to learn to determine which digits in the number are considered significant. That means would be used in determining how many sig figs we have in our final number and which are not. Okay, well, all the whole numbers are considered significant. So if we look at this number, I'm going to go through this whole listing of rules, and then I'm going to break it down, even make it even simplified for you, where you ask yourself a couple of questions. Okay, and depending on how your answer would tell you whether it's significant or not. All right, so all whole numbers are significant. So numbers 1 through 9, no brainer, significant. So this number, 4,892.2, 95.2 has 5 significant figures. Okay, because all of them are whole numbers. Where the confusion comes into play is the zeros. Okay, so the rules of significant figures say that the leading zeros of any number, in this case, any number less than 1, that's what this is, right? 0.000 are considered insignificant and do not count as being significant. Okay, and so the first 4 zeros up front are not significant. All they're doing is holding the decimal place. That's it. Giving you a decimal place. Then the other digits, being whole numbers, rule number 1, make them significant. So this number has 4 significant figures. Okay. So leading zeros do not count. Where the zeros are placed someplace else could be confusing. When they're considered what's called captive, meaning that they are in between 2 whole numbers, they are considered significant. So this 0 in 3050 is significant, whereas the last 0 is not considered significant. Okay, it cannot a captive 0. So 3050 has 3 sig figs in that number. Okay, the next number, 0.00, well, refer to rule number 2. It's a leading 0, so they don't count. And then you got other zeros. They're in between 2 whole numbers, so they count. So 0.002001 has 4 sig figs. Okay, 4 sig figs. Okay, and then trailing zeros can be confusing, but the thing to remember is this: for trailing zeros, if there is a decimal point anywhere in that number, then the trailing zeros will count. Case in point, first one, 0.0880. Well, the first 2 zeros are leading zeros, rule number 2, so they don't count. So the last 0, questionable, right? Do they count? Do they not? They're not captive. Okay, but they have a decimal point in that number, so therefore that 0 counts. Okay, unlike the next number, 28,500, where there are no decimal points in anywhere in that number, and those zeros are not captive, they're not surrounded by other integers, so they don't count. So there's 3 sig figs. Okay, now to kind of maybe streamline it a little bit, okay, you might ask the question. All right, let's take a number like 200. Okay, we know that 2 is a whole number, and so all integers count. So we got 1 sig fig for sure. Question is, how about the zeros? Now you can use the rules, and that's fine, or you can ask yourself the question. 2 questions. 1, for these zeros, is there a whole number integer in front of them? And the answer is yes. Okay, question number 1. Question number 2, is there a decimal point anywhere in that number? Answer is no. Therefore, those 3 zeros are not considered sig figs, so this only has 1 sig fig. Okay. So for these 2 questions, if you answer no for any one of them, then those zeros don't count. Let's take leading zeros. If you forget the rule about up here, okay. Okay, take these 3 leading zeros. Question number 1, is there an integer in front of these 3 leading zeros? Answer is no. Don't have to go any further. Those leading zeros don't count as being significant. Okay. All right. The 0 in between the 1 and the 2. Okay, the fact that it is captive would tell you yes, they are. But in case you forgot, ask the same question again. Question number 1 for this 0 here. Is there an integer in front of that 0? Yes. Okay, so that's good. Question number 2 for this 0. Is there a decimal point anywhere in that number? Answer is yes. Okay, I got 2 yeses. That means that 0 between the 1 and 5 counts. All right. Repeat the questions for the last 0. Is there an integer in front of that last 0? Yes. Is there a decimal point anywhere in that number? Answer is yes. So therefore, that 0 also counts. So this number, 0.001050, has 4 sig figs. Okay, see how that works? Oh, got a couple of questions here, sorry. All right. I don't know, Erica, I don't know your question. What are you asking? Oh, it's an accident. Okay. No worries. I was trying to decipher it. All right, so the last number here. Now, once you have a number, and if you want to, once you add a decimal point and you add zeros, then those zeros automatically count. Okay, so 285.00 has 5 sig figs. That's the same question. So those last zeros. There's a decimal point in there. There's an integer in front of them. Yes, yes. Therefore, they count. Okay. All right. Now, some numbers are considered what we call exact. You know, like when you say 14 people, that's exact. It's not 14 and a half, 14.1, it's 14, an exact number. The conversion factor, there's exactly 3 feet per yard. There's exactly 100 pennies per dollar. There's 5 of anything, iPads, 12 pack. Those numbers are considered exact, and therefore will now play a role in determining how many significant figures your final answer will have. Okay. All right. Things that are measured, any measurement, 7 inches, 200 pounds, 10 ounces, those are measurements. And anytime you have a measurement, there's always a degree of uncertainty because the piece of equipment that you use to measure that is not 100%. Okay. There's nothing, to my knowledge, that is 100% accurate with respect to measurement. Because once you get to 10 decimal places, there's always 11 decimal places that you can go. Right. So there's always the degree of uncertainty. Right. So any measurement is not exact, and therefore not being exact will play a role at the final end when you actually give an answer with the correct number of significant digits. Okay. For example, where we say about 5.05, how many sig figs do we have in that number? Anybody want to take a shot at that? 3, exactly. Okay, you got 3 sig figs and 5.05. You all see that? Okay, that 0, you know, use the rules. They're captive between 2 whole numbers. That's fine. That's good enough. But if you forget that, you know, there's an integer in front of that 0, and there's a decimal point in that number. So yes, it counts. How about the next one, 1200? We got 2. Okay. Not 4. Think about it. Ask the same questions for the 2 trailing zeros. Is there an integer in front of those 2 zeros? Yes. Is there a decimal point anywhere in that 1200? No. So those two digits would not be counted in significant digits. So I got two sig figs. All right, how about the next one? 0.02020. And how many do you think? We got four. Nope, three. Nope, we got five. Okay, the answer is four. Think about it now. Remember, remember, these up front are leading zeros. But again, I can't overemphasize it. I'm sounding redundant, but it must be a reason, right? Ask the question, is there an integer in front of the zero? No. Once you got to know, you don't have to go any further. Those don't count. Okay. This zero in the middle between the two. Well, the captive zeros count. Okay. But if you forget, ask that question again. Is there an integer in front of that zero? Yes, there's a two. Is there a decimal point? Yes, I got yes, yes. And the same thing for the last one. Okay, so I got four sig figs. The next one only has one. Okay, those 0.000, those leading zeros don't count. They're just showing you a decimal point. But again, there's no integer in front of those leading zeros. So you got a no answer, so they don't count. How about 50? 50. How many sig figs do we have there? Okay, you got a one, exactly. Same reasoning for the 1200 for that zero. Now, the moment you put a decimal point in there, how many sig figs do you see at 50.00? You got four exactly. Notice between the two numbers, you might think I got 50 and I got 50. However, the 50 measurement could have been an eyeball measurement where we just guesstimated, all right, it's about 50 feet. See, it could be 49 feet, it could be 51 feet. But the 50.00, now we had an instrument that's a little more accurate than in place. So the 50.00 is a lot more precise than the 50 by itself. Okay? All right. And then the 123.45, obviously, all of them are integers. Okay. Jessica had a question, just to recap, the 1200 and the 50 are two, that's correct. And the one sig fig, because the zero is at the end and then in the middle somewhere. Right, that is correct. For the 50 and the 1200, which is that one and that one. Okay, those zeros there. Okay, they're creating zeros. And there's no decimal point in anywhere in that number, so they don't count as being significant. Same is true for the zero here. But if you look at these zeros for 50.00, there's a decimal point in that number and there's an integer in front of them, so they count. Okay. And then obviously the 1 through 3.445, all of them are integers, so they all count. And then finally, the last one, we have three digits in there. Now you might say, well, what's the point of all this? Well, I'm glad you asked. We're going to add, subtract, multiply, divide. Okay. Now, for multiplying and dividing only, we break it up in two groups. For multiplying and dividing. And if, for example, okay, we are going to multiply these two numbers, 5.05 and the 1200, or we're going to divide it, these numbers, to make a difference whose numerator does. Our answer, our final answer, should have no more than two sig figs. Okay, why? Because the 1200 is the least accurate number between these two numbers. If we did the same thing with these two numbers, let's say we multiplied 4 before we divided, okay, our answer should only have one sig fig because the 50 is the least accurate measurement. Remember, the whole point of all this is to present a value, a number that is no more accurate than the least accurate measurement that you have. Okay? Now, when we add and subtract, we're going to be dependent on decimal place. We'll get to that here in a bit. So multiplying and divide only. The number, the final number that you present cannot be more accurate than the least accurate number that you used in the mathematical function, whatever it was. I know you can plug these numbers in the calculator and you can get a whole slew of numbers, but that doesn't mean that is the correct number to present your answer in. Okay, this is kind of a brief summary to kind of help you out with, determining the zero. Is it, if that zero is, it's straightforward. I'm thinking here. If you're unsure about that zero, ask those two questions. Is there an integer in front of that zero? Okay. And is there a decimal point anywhere in that number? If you get a no for any one of those questions, then that zero is not counted as being significant. It is significant with respect to the value, and it's where it's at to give us a decimal point, but it's insignificant when it comes to the final answer. You might be wondering why I keep repeating it. It's for a reason. Okay, when we start rounding numbers up. Okay, and you'll see here in a second. Okay, because now we're going to talk about rounding numbers up. Now, the technique we use here at got a question. Which of these is more accurate? Which one of the 1200 and the 50? Is that the question, Karen? You have a question? If I were to write which is the least accurate? More accurate. Well, with respect to measurement, the 1200 and the 50 have the same accuracy because they don't have any decimal place. They were maybe measured by, I don't know, it depends, a very crude measurement tool. Okay, because if we were using an accurate ruler or a tool, we would get a tenth of a point, a tenth or 100th decimal place. Okay, but with respect to presenting your answer when you multiply and divide, then your answer should have no more than one sig fig, because the 50 only has one sig fig and the 1200 has two sig figs. Okay. Oh, okay. 50 versus, the more accurate would be the 50.00 because you're going to more decimal places. Okay. Yeah. Did that answer your question here? Yes. Okay. Okay. Rounding. Okay. Because we need to learn how to round the number. Now, we do the multiplication and the division, and we get this humongous number. And like I stated, well, we don't want to present that number because it will be inaccurate. Okay. So we got to learn where to round the number and where to truncate your answer. But before we do that, we're going to learn about rounding. Okay. So what we do is this. We look at the number that we need, the decimal, let me restate it. We look at the number that we need to truncate. Okay. Now, one or two things are going to happen. That number is either going to be rounded up or it's going to remain the same. And what we do is we look at the immediate neighbor. We don't care about that number 4 or 5 digits down, only the immediate number. And we look at it. And if it has a value that is less than 5, then that number that we're going to truncate it at stays the same. For example, if you look at 5.4, we're going to we're going to truncate it at one significant digit, which is the very first number, one digit, which is 5. Okay. So we look at the neighbor. Okay. And we determine that it's less than 5, which tells you that that number 5 remains 5. Now you could have a number like, for example, 6, 2, 7, 3, and you might be tempted to say, well, okay, I'm going to truncate it here. Okay, but I got a 5 here. I'm looking at the neighbor, but it's next to a 6, so I can bring that to a 5. And no, we don't care about what's down there. We just need to know the value of the immediate neighbor to the right. That's it. Okay. So this 5.4, we're going to round it to 1 sig fig. So the answer you present is 5. If we look, if that number, the neighbor is 5 or greater, then that number that we're going to truncate gets rounded up to 6. So 5.5 becomes 6. We don't drop the number. That number is either going to stay at that value or go up. It will not go down. Okay. And we don't want to change the magnitude of the number. This is important. Okay. For example, let's say we want to round to 1 sig fig, the number 5400. 1 sig fig. Okay, so the 1 sig fig position is right there, the very first number. Then the 2 sig fig position is the next number over, so on and so forth. All right, so we look to the immediate. Okay. That 4 is less than 5, which means that 5 stays as 5. What happens is that 4 now gets converted to a 0. Okay. We don't drop the numbers because look at the magnitude. The number that you begin with is in the 5,000 mark. And what happens occasionally, people tend to truncate the neighbor and everybody else with it. And so look, it's 5,000 versus 5. You know, if you were asked to, you were going to give you, put a dollar bill in front of this, $5,400 versus 5,000, which can you see how by dropping those zeros, you change the magnitude in the whole value? So no. So the thing to remember is this. Any numbers before the decimal point, wherever the decimal point will be, like this number here, all the numbers that you're going to, you might be tempted to drop, you convert those numbers to 0. Any number after the decimal point, just get rid of it. Okay, you don't need to worry about it. Let's try it this way. 5400.1. Okay, and we're still got to go to the 1 sig fig. Okay, so same scenario. That becomes 5, 4, 0, 0, 0. Okay, we don't go 0.0 because what have you done by converting that 0 after decimal point to 0? How many sig figs does this have now? 5,000.0. How many sig figs is that? 5000.0 is now how many sig figs? 5 exactly. And the problem said to convert to 1 sig fig. And so by making that, putting a decimal point in and converting that 1 to 0, you have created accuracy that you don't have to begin with. So that would be incorrect, right? And so the thing to remember is the numbers before the decimal point get converted to 0, any integers, and the numbers after the decimal point get dropped completely. You don't want to change the magnitude. All right, let's do a couple of examples and then we'll stop it here. All right, here the question says, round out to 3 sig figs. Well, to do that, what we got to do first is find the 3 sig fig position. So starting from the far left, count the 3 in. So starting at 1, we got the 3 is the 3 sig fig position. That means the numbers 7 and 4 are going to be dropped. The question is, does that 3 remain at 3 or does it get kicked up to 4? Answer that by looking at the neighbor, which is greater than 5, which means that that 3 becomes 4. Okay. So the answer is 8.14. Okay. We got 7,162 and 32 cents. All right. We got to round it out to the 3 sig fig numbers. So we find the 3 sig fig position. Okay, starting far left of the 6. Okay. Now keep in mind we got point and then some numbers. So the numbers after the decimal point get converted, dropped. And the numbers before the decimal point, like the 2, are going to be converted to 0. Look at the magnitude that you're in. You're in the 7,000 range. So our answer should be in the 7,000 range. Okay, so we look at the neighbor. Neighbor is 2. That means the 6 remains at 6. The 2 gets dropped, converted to 0, and the 0.32 get dropped. If you drop the 0 and the 0.32, guess what you've done? You change the magnitude. You're in the 7,000 range, not the 700 range. Next one, go to the 3 sig fig position. Remember the zeros don't count as being significant. So the one after the 3, that is a 3 sig fig position. And so we look at the neighbor, which is 1, which tells you that that 1 at the 3 sig fig position remains a 1, and everything else is dropped. So that is the answer. So these are examples of the answers that you have in your calculator, and you did a multiply and a divide, and now you need to make sure you get the right number of sig figs. So your answer could be 0.001311154 on your calculator, but the number you did your math with only had 3 sig figs. So your answer should be no more than 3 sig figs. So that's how you will present your number as 0.00131. Okay. 24,925. Okay, keep track of your magnitude. You're at the 24,000 range. Okay. 3, look at 9 is a 3 sig fig position. So that means you look at the neighbor, which is a 2. That means the 9 remains a 9, and the 2 and the 5 get converted to 0. Okay, don't get dropped, because if you drop them, now you change the magnitude to 249 versus 24,900. Okay. So key points: drop numbers after the decimal point. Okay. And numbers before the decimal point get replaced with 0. And I should add point number 3 is keep track of your magnitude. All right, don't change the magnitude of your answer. And you see that? This will be incorrect. And a lot of times I might get, I don't understand the magnitude. Well, very simple. The dollar symbol in front. Okay. Everybody understands money, right? You got 24,900 versus 249. Isn't there a big difference there? Big difference, right? Yeah. All right. So don't change the magnitude. All right. So I tell you what, we are chapter 2. Why don't we stop it here? I got 2:15. And we will continue on Thursday.